and Howard are on Wurundjeri land. They've all cared for and managed these lands in a sustainable and responsible manner for many tens of thousands of years. When the initial settlers came across the Western districts, they commented that the axles of their carts and their horses sank into the friable soils and turned over bushels of bulbs, and the grasses reached their saddles. In other areas, they described the land as like a gentleman's park. We need to respond to their welcome to country by also truly caring for this country. We have much to learn from them, not only on their land, farming and fire practices, but also about their governance, which led to no major wars across this continent for many tens of thousands of years. I offer my respects to their elders, past, present and emerging, and to all of their mobs, and to our people from other mobs attending today, and to all of you who have logged in from near and far. Hi, I'm Rob Gardner, and I help support these meetings with Chris and Howard. Today, my particular thanks to Chris, who is managing all the activities in the background. Firstly, some housekeeping. Tonight's presentation and Q&As will be recorded and available to download in a few days' time on the Renew website. If you've got any technical problems or general comments, please use the chat button, which is the bottom left on most computers. If you have a question about questions, enter them at any time using the Q&A button, which is in the bottom right. Keep the questions fairly short if possible, please. We usually have a lot of questions, so we'll probably consolidate similar ones and then cover as many as possible in the time available. Some of the names are new to me. Maybe you're new to Renew, which was formed in 1980 to promote sustainability in all its forms. It's best known for its two magazines, Renew and Sanctuary, but also events such as Sustainable House Day and Speed Date and Expert. Also EV fairs and attending many other fairs and events. However, it also has a significant research section and a lobbying group, 3 modelling packages, Sunnilator and Tankulator, and also an advisory service aimed not only for households, but for business and governments. Tonight, we are very fortunate to have Shama Islam from Deakin University in Geelong to make a presentation before an extensive Q&A session. Dr. Shama Islam is a senior lecturer in electrical engineering at Deakin. She's a leading researcher in the areas of IoT for smart energy applications, optimum energy management, energy data analytics, and smart grid security. In 2015, she completed her PhD from ANU. She's been an investigator in a number of ARENA-funded projects. She's received the Future Women's Leader Award from Monash University in 2017, and also been awarded the Victorian Fellowship 2019 for her contributions to scientific innovations in Victoria. For this project, she was funded by the Geelong City Council to implement a pilot-scale demonstration of energy use optimisation technologies. And tonight she'll explain the details of this program and the findings they found from such an analysis of household usage, control and optimisation, and the substantial savings achieved in 2022. So that's all for me, and I'll pass you over to Shama.
Thanks, Robin, for the introduction, and many thanks to Renew Melbourne Branch for giving me the opportunity to talk about this project, about which I'm very passionate. So I'll start sharing my slides, but I would also like to make a note, like if for any reason, if you lose my audio at some point, please put a note in the chat window so that like I can take an alternative of that. So I'll just share my screen. I hope all of you can see my slides.
If you just make it full size, Shama.
Yes, I'm making it full size. Yeah, now it's full size. Can you see it full size now?
Yes.
Thank you. Today I'll be talking about this energy optimization project for Geelong households. When I started researching in the area of energy systems and more on the energy efficiency sides, then one thing that always came to my mind that what is causing some power outages, which I have experienced over, let's say, 2016, 2017 kind of time period. And I realized that we have enough generation to meet our demand. But what is happening there, like if everyone is using their appliances at the same time, the distribution line, which provides the electricity to our home, their capacity may not be sufficient to manage that load. So it's more like a traffic congestion problem. What can be done in this regard? I've realized that there are many appliances in the house whose operation can be deferred to alternative times. For example, you can choose your washing machine to work at a certain period of time, so that like it manages the washing and prepares the clothes for you within a certain time of the day. It may not be true for all appliances such as stoves or even like heating, cooling in some cases, but for many appliances, it may be applicable. And if we can do this kind of scheduling, we can manage the electricity demand more effectively. As a result, we can reduce the load demand during peak hours, which is usually the late afternoon to early evening periods. You may know that the tariff can be higher during these peak demand hours, especially if you're in using a time of use tariff. And in that case, if the load demand can be reduced during those high tariff hours, the electricity bills for the users can be reduced as well. Another benefit is like if these appliances can be scheduled at optimal times, then the occurrences of electricity outages can be reduced, which is a very significant benefit if we can achieve this optimal energy use, and it can serve as a way of demand response. Now, the other question that came to my mind, that how does solar play in this energy optimization problem? If you talk about like making households energy efficient, the first thing people think about is installing solar panels in their houses. And obviously, that's a very good way to achieve economic savings and providing a sustainable way to meet the energy demand. However, a user may not extract the maximum benefits of solar panel installation if the user does not have sufficient load demands to consume that solar generation. And often, the maximum demand periods do not coincide with the maximum solar generation periods. You may have your maximum demand during late evening hours, whereas your maximum solar generation occurs during morning periods. So an optimization algorithm will be required, which can schedule the appliances during high solar generation periods. And it has to be done optimally and in an automated manner, rather than like suggesting the users that you can use your appliances in this time or that time. So the idea is to promote more self-consumption and less exports. This is an important consideration for the distribution network operators, because you may have heard about this, that the distribution network operators often try to put a limit on the export the solar panels can have to the grid, because this helps them to manage the network voltage issues and so on. So if we can reduce the exports during the the morning hours, that can be another co-benefit as well. One thing to note is that we need to forecast the solar generation accurately if we want to achieve this optimization in a true sense. Otherwise, our optimal solutions may be less accurate. So that is something to consider. Now, we have agreed that we need to have an intelligent algorithm that can schedule the appliances based on the fact that when our solar generation is maximum, so that these appliances are able to use the solar generation during most periods of the time. But how this can be integrated in a household? We all know that in Victoria, each house is equipped with a smart meter, maybe at the taxpayers' money, but they are there. So these smart meters are intelligent computation and communication devices, but they're primarily used for billing purposes. So though we have smart meters at our homes, we may not be realizing the true potential of these smart meters, what they can do for us. So these intelligent optimization algorithm can be integrated with the smart meter, and which can control the user appliances within the house. So this algorithm will be able to coordinate with external data servers for services such as weather, solar generation forecasting, and it can use that existing smart meter communication infrastructure for that. So there is a benefit of integrating this algorithm with the smart meters that we have at our home. So overall, we are going to achieve an Internet of Things or IoT-based energy efficiency solution by allowing all the appliances within the house to be able to talk with the smart meters directly, and the smart meter to be able to control those appliances. So overall, everything talks with each other, which is the key idea of an IoT-based solution. So we started working on this problem, and initially some proof of concept work was taken by Deakin University's final year project students. And when we found that there are some results coming in and we have a confidence that this might work in a real scenario, we approached Geelong City Council through Clean Tech Innovations Geelong by submitting a proposal, and received the funding from that scheme. So at the beginning, I would like to acknowledge the support of the City of Greater Geelong, the Geelong Manufacturing Council, and the state government for funding this pilot study for households in Geelong through Clean Tech Innovations Geelong. And I would like to acknowledge the continuous support from Nicholas Phillips. He's the technical head of sales in Itron, Australia, who provided valuable advice regarding the implementation architecture and who helped me with the integration of weather forecasting platform. So Nick and I have been working on this idea for nearly about 5 years now. So we thought about expanding this collaboration further and making this idea a reality. So this is the story, the background story behind how we started this project. So at the beginning, we wanted to recruit some participants in the houses where we want to test our prototype. So we circulated a simple survey in a number of media platforms from the Geelong City Council and Geelong Sustainability. There we asked some questions about the electricity use patterns and whether the users are interested in automation products. For example, we asked like what type of appliances the user has, whether they have dishwasher, washing machine, tumble dryer, whether they have solar panels, battery storages, also like what type of tariff structure they have, whether it's flat rate or time of use tariff. We also wanted to ask like if there will be someone at the home during daytime who will be able to control and monitor the appliances, how they are working and so on. And usually because it was the COVID time when we circulated that survey, it was an easy answer because usually there was at least one person at the home during the day for whom we have circulated this survey. However, the most important thing that came out of the survey is like whether the users are happy to allow flexibility in their everyday appliance usage patterns. Not everyone will be able to allow that flexibility, but for our prototype to test, we need those cases where users will be able to accommodate those changes. And then based on the user responses to these pre-screening questions, we selected 20 households, but at the end, only 8 households could participate because of different issues, which I'll talk later on. And for these 20 households, we have prioritized users who have solar panels. This is because we could not find any user who has time of use tariff. So our prototype to give you cost savings, we need the user to have either solar panels so that they can get the cost savings from using solar generation, or we need users to have time of use tariff so that we can schedule the appliances during a low price time period so that the users do not consume more energy during high tariff period. However, if the user does not have solar panel and has a flat rate tariff, there may not be any cost savings for the user, though there can still be electricity savings, especially during the peak demand hours. Other features that we have about our participants is that 75% of them has not used any home automation before, and 50% of them has not used any energy consumption monitoring app. So you may imagine that at the early stages of the project, we needed some time to educate our users about how we are going to apply this energy optimization, what we are going to do, what sort of facilities we need to use, such as the Wi-Fi and those kind of things. So we needed some, we need to put some effort in explanation of those, the preliminary things. In terms of the appliances, all users have washing machine and dishwasher, and 62.5% of the participants have tumble dryer. So some of the features of the appliances and the solar panels you can see from here. Most of the users have solar panel capacities between 5 to 7 kilowatt, which is common for a residential scenario, though one user has a very higher solar panel capacity, greater than 9 kilowatt. The typical washing machine start time used by most of the users is like any time in the morning, with no like specific preference on the operating time of the washing machine. The washing machine of the users that we considered, their energy consumption is in the range of between 1 to 3 kilowatt hours, with most users having the cycle power less than 1 kilowatt hour. The typical wash duration for most users was 1 to 2 hours. And this slide shows you the key features of the dishwasher. The dishwasher typical start times for most users is late night to early morning, the 9 p.m. to 5 a.m. time period. And the energy consumption of most of the dishwashers were in the range less than 1,000 watt for the cycle power. And the typical wash duration that was in the range of less than 1 hour for some people, but for most people it is 1 to 2 hours, which can be expected. Then for the tumble dryer features, the start times for the tumble dryer is mostly 3 to 5 p.m. for most users, though some users are using during the early morning or afternoon periods between 5 a.m. to 3 p.m. The energy consumption of the tumble dryer was quite high. It can be from 1,000 to 4,000 watt or more than that. Though for most users, it was between this range, 1,000 to 3,000 watt. The typical duration was 1 to 2 hours for most people, as you can see. So these are some of the key features that we collected from another set of questionnaires from our participants, because we wanted to know how their appliances are operating, what energy consumption they have, how long they will operate, and when do they normally turn on the appliances. So we tried to capture the user behavior, the user energy consumption behavior through these statistics. We also collected the information about the typical electricity demand of the users. So this will be the average demand profile of all those 8 participants. And you can see that some users will have this evening peak, and some users will have this early morning peak around 5 a.m. or then around 5 p.m. Okay, so this was our average demand profile based on the information of the user demand between 2019 to 2021, which we used to inform our study that how the typical user demand looks like, and if we alter the energy consumption of a certain appliance, how this might affect this overall demand profile. So this is the gross demand profile without taking into account the solar generation. This is the peak demand scenarios for all the participants. So as you can see that this peak demand varies between 0.5 to up to 1.3 kilowatts for some users. And the occurrence of the peak demand, when do they occur during the time for different participants? You can see that for some participants, it occurs during the evening, late afternoon time period, 7:30 p.m. or 5:30 p.m., 5 p.m. And for some other users, the peak demand is in the early morning period, such as 5 a.m. or 7:30 a.m. So you'll notice that here we have specified the participants with their IDs, which starts with participant 3, participant 4, participant 5 in that way. We don't have the other participants. So the IDs, when we apply them to the users, this was from the original scenario where we have all the 20 users, but then not all of them could participate in our study. So we continued with that, whatever the IDs we have. Okay, so this was the peak demand. So this slide shows you the conceptual model. So we have the weather forecasts from the external server, which is communicated with the intelligent devices within the houses, which can be a microcontroller. And this microcontroller then computes optimal decisions to turn on or turn off the smart plugs here. And then these smart plugs will then turn on the devices. So that was the basic idea of this energy optimization tool or energy optimization prototype. And this is the broad architecture of our solution. So we have weather forecasts from a platform which are stored in the secured file server. And from the secured file server, the weather data is read by the Raspberry Pi microcontroller, which computes what should be the best time to operate a certain appliance within the day. And then it stores these optimization outcomes again in that secured file server. In the morning, the microcontroller will send some SMS notification to the users, showing that like how they should turn on their appliances at different times of the day. And according to these optimum appliance schedules, the Raspberry Pi microcontroller will turn on the smart plugs, and then these smart plugs will turn on the end user appliance, whether it's a washing machine or dishwasher, and so on. So this is the brief solution architecture. So during the trial, each household received a Raspberry Pi microcontroller and a smart plug, which turns on an appliance during a certain time at the day as computed by the microcontroller. And these solutions are computed on a day-ahead basis. So usually later at the night, around 11 p.m. or so for the next day. And they use weather forecasts from a secured file server. And we also needed the historical demand data, which we previously downloaded from the PowerCore My Energy portal. So at the early morning, around 5 a.m., the participants are notified about the best time to operate their washing machine, dishwasher, and tumble dryer. They would also get notified about whether there is a chance of rain, which might help them to think about whether they want to use their washing machine or not. The pilot continued for at least 2 months for each participant, and the trial it took place between the time period February to October in 2022. The reason why we took a longer time period than 2 months for overall is because the council wanted us to like try this prototype for the houses one by one. So first we try with one house, and after it is completed, then we try with another house, and so on. So that's why it took a bit of time to complete. Another thing to note is that the users are given the option to override the optimal schedules. The users were given instruction that they can turn off the smart plug or turn on the smart plug by themselves. And then that way they can override the schedules if they need to. But we have also requested the users that, if possible, stick with the optimum schedule so that we can identify whether our algorithm was successful to achieve the savings in energy consumption. Note about our weather forecast method. So our approach uses forecasts generated by National Aeronautical Information Processing System, which uses weather forecasts from the nearest airport, that is Avalon. And this is the forecast used by BOM as well. And we also utilize temperature forecasts of Geelong from Willy Weather to improve our accuracy. These forecasts are generated at around 11 p.m. for the next 24 hours. And we also tell to the users about if there is a chance of rain. We are planning to improve this weather forecast method further by using a cloud movement sensor, which can predict the movement of cloud ahead of time, and which will be helpful in finding out the solar irradiation more accurately. And we plan to consider this improved forecast in our future studies. So what does our prototype include? It includes a Raspberry Pi 3B microcontroller and a TP-Link CASA HS110 smart plug. So at this stage, we controlled only one appliance, which is the washing machine, but we could also control the dishwasher or tumble dryer, but we could not do multiple appliances at the same time. though we plan to extend this for multiple appliances simultaneously in future studies. For sending text notification to the users, we used Vonage API, and the text messages were sent from the Raspberry Pi microcontroller to the participants' mobile phones directly. And the prototype uses home Wi-Fi to connect, and the control operation is executed completely locally within the household. So we do not have a remote control in this case. The control is done locally. This is one important feature of our prototype. So it basically communicates with the external servers for weather forecasts, and that's a secured file server again. But other than that, all the computation is done locally within the Raspberry Pi, and the control is also within the household. So there is no other external thing involved within. There is no cloud-based control here. Another interesting feature is that this solution does not cost more than 200 AUD. However, there can be some ongoing costs for maintenance. If something goes wrong, let's say the smart plug is not operating, or the Raspberry Pi has turned off, or it is not getting connected with the network, then someone will have to go and look what's happening. So there might be some costs on that. And also, like if the user wants to receive text notification, there is a cost of using that API for text messages. So I have included a short video here for showing us like how this approach will work. This is a conceptual video, not an exact video, because then I'll have to wait for a couple of hours to show how it looks like when it's working in the real-time system. So hope you can get this sound. Check if it is not working. I'm not sure why the video is not working. Oh, it's there. If you cannot hear the voice of the video, just let me know. I'll check again.
I can't hear the voice.
Okay, sorry. Then I think I'll have to reshare with the sound. Give me one moment. I think I have shared the.
Over the night, the Raspberry Pi at your home
Good.
will compute the optimum operating schedules for the appliances. Now the sun is up and shines through the day. Now is the time for your solar panels to heat up. Let's say your solar panels are producing enough energy to heat up the appliances at your home. And some optimum operating schedules are sent to you via text notification. As you can see that the optimum operating time for washing machine is shown as 10 a.m. Let's say you have a washing machine connected with a smart plug, which can make sure that your washing machine turns on just at the right time. Now it's 10 a.m. Now your smart plug will be turned on by the optimization algorithm so that your washing machine is ready to use the optimum time.
So that was like just a conceptual video, like how this approach will work and so on. So now let's have a look what benefits we had like after implementing this project through some of these evaluation results. So this figure that I'm showing here is the net energy consumption for the participant number 5. And this shows you the comparison of the energy consumption between 11th March to 12th May. So the blue graph shows before optimization, and the orange graph is the after optimization. So one is the 2021 when we did not have this control, and when we have the optimization prototype here in 2022. And you can see that the demand, the net energy consumption has been reduced significantly. These morning peaks are now much smaller. And we could shift many of our energy usage to this high solar generation time periods. And as a result, you can see that the reverse power flow, it reduced during 9 a.m. to 2 p.m. time period, where there was a much longer time period of reverse power flow here in 2021. The net energy consumption decreased by 1.5 kilowatt hours. So originally it was 5.3 kilowatt hour. And then after installing the controls, it was 3.8 kilowatt hours. So if you take the difference between these two and divide it by the original amount, then you get this 38.8% savings on an average day. So if you compute these savings for multiple days, you can then identify like how much more savings you can achieve. I have not calculated the cost savings here, but you can readily multiply your electricity tariff with this 1.5 kilowatt hour to get an idea that how much will be the savings for a single day, for a month, for a year, and so on. We also noticed that the peak demand decreased by 48%, which is equivalent to 0.62 kilowatt hour. And the peak shifted from 5 a.m. to 8 a.m. That morning peak is now here. Though we cannot see it here because it is now covered by the solar generation, and because we're showing you the net energy consumption here. And then what is the optimal operating time of the washing machine for different participants? We have shown some slides to show you those results. For some of the participants, there is a clear best time for using the washing machine. For example, for participant 3, we found out that the best time in most cases is 9:30 a.m., where the preferred time was 9 a.m. So you can see that the optimal time and the preferred time were pretty much close. And some of the users may already be using their appliances quite thoughtfully, which might be reflected in this scenario. This participant is operating the washing machine in 43 days during the optimal times. In some days, the participants will not use washing machine. In some days, the participant may not be at home, or they might be using it in a different time because of their other commitments and so on. And these results are based on the trial continued between March to July in 2022 for participant 3. And this one shows you the optimal times for participant 10. And clearly you can see that 11:30 a.m. was the most frequently selected optimal time by the algorithm for participant 10, and the participant's actual preferred time was 11 a.m. So they're again very much in symphony. So this trial was between April to September, which is pretty much the winter or early spring time period. And the participant operated the washing machine in 69 days during the optimal times. In some cases, we got 2 different times, which can be equally good or nearly equally good. For example, in this case, for participant 4, it can be in some days the algorithm decided that 10:30 a.m. is the best time to use the washing machine, whereas in other days it decided 11:30 a.m. whereas the participants' preferred time was 10 a.m. And this trial was between May to September, among which 53 days were used by the user during optimal times. Another case with 2 different times is this participant 12. You can see that 9:30 a.m. and 10:30 a.m. Both are chosen nearly equally by the algorithm as the best time to operate the washing machine. And this trial was between February to May. And in this case, the participant preferred time was 11 a.m., but the earlier time period was selected by by our algorithm. This could be because the trial started in late February, and even during that time period, it was end of summer or the beginning of autumn. So even during that time, the early morning periods may have a better solar generation. So that's why the washing machine optimal time is selected earlier in the day rather than later in the day. In some of the cases, the algorithm selected an optimal time for a wider range of time. For example, for participant 5, you can see that in some days it's selected 9 a.m., in some other days 10 a.m., or some days 12 p.m., but mostly during the early morning periods for the user. For participant 5, the preferred time was 9 a.m., and you can see that it was either 9 a.m. or 10 a.m. as decided by the algorithm. And if you also remember, this participant 5 has an early morning peak, which could also be a reason like why the appliances are scheduled during different time periods of the day. And this trial also continued between March to May, which is kind of the late summer, early autumn period. And here is another case for participant 9, which also continued between April to August, the winter time period. In this case, the user has a preferred time as 10 a.m., but you can see that most of the days, as computed by the algorithm, the optimal time was selected as 12:30 p.m. It could be because of the winter period where the sunshine is usually at a later time period of the day. And another thing could be because this participant operated the washing machine in only 21 days. And it may not be reflecting, we may not have sufficient data to reflect that kind of insight, as we can see from the other cases. We did not show the results for 2 more users because of insufficient data. In some cases, users may not be using the smart plug as we have suggested them to use, and may not be using washing machine because of unavailability or some other reasons. However, by seeing that key results from our evaluation, we have realized that one of the significant benefits of our algorithm will be the reduction in energy consumption, and it can be used for peak shaving applications in residential energy consumption. This can reduce the reverse power flow and ensure less stress on the electricity network assets, and can cause co-benefit for the distribution network operators. And through this trial, as we communicate with the different participants, we suggested that these notifications of the optimal operation times help them to modify their consumption behavior, and they are now thinking more about how they can better use the energy, which is a very exciting thing for me, because I never realized that how notifying the users about their energy consumption can cause such a big change in their energy consumption behavior. The tool also demonstrates how solar generation can be best utilized by suggesting strategies to the users by promoting more self-consumption. And in that way, we promote the uptake of solar panels, as people will be able to see how solar generation can help them reduce their energy costs. It also has a quicker return of investment, which will be less than 2 years, as we already said that it is a very low cost solution in our earlier slides. Some of the challenges that we faced during the implementation. The first challenge was when our equipment got changed. Initially, we planned to use Itron's IoT development board, but they were originally in USA and they could not arrive due to shipment delays during COVID. So we had to change our solution to Raspberry Pi boards instead. But remember that we can extend this approach to any other microcontroller type. So there is no such limitation that we have to use this one or that one. We also had delays due to equipment delivery and some other things, and the testing got delayed. And as a result, we could not approach the participants before 2022. And due to these delays, many participants' circumstances change, as you can imagine. Some people have moved out of houses and their new houses do not have solar panels. And by the time the solar panels installed, our project may have finished or so on. And as a result, some of them were not anymore available for the study, and some people may have chosen another energy efficiency solution and may not have the time to test another our optimization solution. So things happen like that, and that was another challenge that we faced. And apart from these delays, another challenge that we had is the access of the data. Initially requested users to share their half-hourly generation and demand data, but many of them were not aware that they could have downloaded this from the My Energy portal. Some of them requested their retailers, and in some cases, they gave me the access from the retailer as well, but not all retailers were happy to share. And it was a bit of challenge, but then later on we managed to download the data and get the access of the user demand data, the historical demand data that we needed for our optimization solution. And apart from those challenges of the implementation, some other limitations of our approach is that we need to use the home Wi-Fi, which means that if there is any network outage, then it will cause an issue with the operation of the smart plug. The Raspberry Pi might turn off or may get disconnected from the network, and someone will have to restart so that the microcontroller can again then talk to the network. Another thing is, we already mentioned the accuracy of weather forecasts, which depends on the bomb forecasts and may not be highly accurate, as you can imagine, especially for an area like Geelong, where we have 4 seasons in a single day. Another thing is washing machine, dishwashers. They have electronic switches. These are not same as the mechanical switches. So someone has to be at home to turn them on manually, though the smart plugs will turn on automatically. Now, we could avoid that limitation by using IoT-enabled washing machine or dishwashers, but many users will not have them. They're still not that cheap that everyone will have them. So at this stage, we needed someone to turn them on manually during that optimal time. But if it comes to the turning off scenario, the smart plug can readily turn that off. Let's say the smart plug is moved by the user to another appliance, the algorithm won't be optimal anymore, because the algorithm was trained for that specific appliance, assuming that the smart plug is connected to that specific appliance. If the smart plug is moved to a different one, then the way it is trained and the way it is being operated, they won't match with each other, and then the results won't be optimal. So the next steps, we are planning to extend this algorithm for heating, cooling appliances such as air conditioners, heaters, or hot waters, which we could not do at this stage. And how we can incorporate battery storages in the algorithm. This is another thing we want to explore in our future implementation stage. Also, how we can control multiple appliances at the same time through multiple smart plugs. That is something we would like to do. And some our users have also gave us feedback about like whether we can provide a range of operating periods rather than a single start time that will be more flexible for them. For example, if we can say that, okay, 10:30 a.m. is the best time, but the second best time is 11:30 a.m. and the third best time is 12:30 p.m., then that kind of range gives the users more flexibility. So this is something which we may be able to accommodate quite easily, and plan to do that in the next iteration. And also like how we can integrate this application with our existing smart metering platform. You may be aware of that smart meters can have an application in them like any other smart devices, such as your mobile phone. Currently, these type of smart meters are being manufactured, and when we have them, it might be useful to integrate this application within the smart meter itself, rather than depending on a third-party microcontroller. And finally, I'm looking for extending this algorithm to community facilities such as community buildings and libraries, which has much higher energy consumption because of heating, cooling, and how the energy optimization can help them. So currently, I'm looking for further funding to execute this, the next steps or the next stages of our implementation study, and hopefully we will be able to improve it further. And I'm hopeful that this kind of prototype can be commercially available within the next 4 or 5 years. So I would like to stop talking about what we have found in the project and what we did, and I'm happy to take some questions from you. But if you also want to get more information about the project or want to continue the discussion, please feel free to send me an email, which is my email address is here. Thanks, everyone. I'm ready to take any questions.
Thank you, Shama. That's very good. And we'll look at the questions. So was the use of clothes dryer versus outdoors clothes line included in the washing machine usage calculations? Washing machine gains could be wiped out if a dryer was used instead of an outside clothesline.
Thanks for the question. We did consider that thing. What will be the difference if the user does not have a tumble dryer or if the user has a tumble dryer? So as I said, like some users have them and some users may not have them. So for users who does not have a tumble dryer, we used to, for all the users, we have notified them about the best time, like the time when there is no rain happening. So we do consider the time periods when rain can happen or rain will not happen, and take that information in our optimization. So this is definitely included. But yeah, in some cases, people already have dryers and they might want to use them rather than the drying line. Yeah.
Yep, fair enough. And from Grace, did you consider turning on and off the hot water system using the algorithm?
Thanks, Grace, for your question. As I mentioned that at this stage, we have considered only washing machine, dishwasher, and tumble dryer. but we are working on that hot water system, how to optimally use that, and we are planning to extend in the next stage. But not many people in our study has electric hot water systems, so we did not consider that as a priority, but I'm happy to consider that in the next iteration of the project.
Good, and please start putting your questions in if anybody's got more questions. I think a few have been answered directly by all of my compatriots. So the next stage, are you getting more? Geelong Council is not very fluid with money at the moment. Is there other sources you are hoping to get access to?
Yeah, I'm exploring other sources, and I've also talked about this project in the National Energy Efficiency Conference last month, and there were some government officials from the New South Wales who were very interested about this project, and they were more keen because they have that time of use tariff in some places, and they're also thinking about the hot water systems much more, and they were asking about these questions as well, like whether we have used the time of use tariff structure, hot water systems, and so on. So I guess there is an interest of extending this algorithm for other applications and other appliances. Yeah.
And it seems to be a reasonable price, because a lot of the systems are around, which I don't know they do much more than yours does, seem very expensive. That would be a fair assessment, would it?
Yeah, I mean, our solution is based on a readily available microcontroller from the market. But in the future, if we can integrate this solution in a smart metering platform, probably we would need to rely much less on the hardware side of the thing, and that can be more advantageous.
And some smart meter manufacturers are willing to get involved with that and are interested?
Yes, I mean, I'm collaborating with Itron, and they have a plan to incorporate those kind of smart meters. These are in discussion with the network operators whether they want to have them or not.
Yeah, good.
I think Grace has asked another question. What appliances we plan to optimize in community buildings? Grace, it will be the heating cooling appliances, mainly the air conditioners, heaters. But I think if the building has a hot water system, I would also like to consider that in my optimization tool.
I have a battery in my house, which is only small. So I'd like to optimize that during the winter period. In summer, it doesn't really matter, because it carries me through the night quite happily. But I want to carry through, I'm on time of use as well. So you could include the battery in that as well?
Yeah, we can also do that. I did not have many participants with battery storages. Again, I decided like not to consider this at this time, but we do have the provision for including those in our algorithm. So we originally developed our algorithm for many different scenarios, but then when we saw that we may not need everything at this stage, we decided not to fine tune them anymore, and like decide only on the ones that we have currently in hand.
And how does it do the calculation when you've got multiple appliances? So there's multiple things you can turn on and off.
Yeah, we choose to optimize the highest consumption appliance first. So for users with tumble dryers, obviously that's the first thing we have to optimize, but then we have to keep in mind that the dryer will have to operate after the washing machine. So yeah, there are some conditions that we have to apply in our algorithm, which will take these things into account.
Okay, and there's another question come up. Does every appliance require a smart plug at the power outlet? And what's the cost of these? And does that smart plug take up extra space, so preventing access to the second socket access? The picture you showed seemed to show that the free socket was partly obscured, and so making it unusable.
Yes, I completely agree with what you are saying. It can cause that issue, that it can have an access issue to the second socket. We could provide with a multi-plug or something in that case, and maybe like avoid that issue. But for the purpose of the trial, we just focused on giving one smart plug to the users. However, if we want to control multiple appliances, we will need multiple smart plugs for each one of them, because a single smart plug won't be able to control multiple appliances at the same time, the way it operates. However, there can be like smart plug strips where I have seen some products in the market that has multiple outlets, and but then the question will be, you may not have your washing machine, dishwashers, everything in the same place, so it may not be possible. So there are these kind of discussions that we have to think about before planning to the next stage. Yeah, so I hope that answers your question.
Yep. From Alex. Yep. From Alex, did you consider the matter in the development? This could reduce the costs, as existing gateways could be upgraded. It could be an alternative and more internationally applicable solution compared to the smart meters. Matter is a collaboration between many IoT device items, such as Samsung, Apple, Google, Schneider Electric, Haya, as many more.
Thanks, Alex, for your question. Yeah, I believe that there can be alternative ways to solve this problem. But the reason why we wanted to use the smart meters is because like they're already in our homes and we are not creating something new. That was the main motivation for considering smart meters to host this kind of application. We could not do it at this stage because still now we are using a Raspberry Pi microcontroller to do it, but then in the future we might be able to have those kind of smart meters where we can directly install this application as a mobile application. So yeah, I mean, but there can be definitely alternative approaches, and there can be other states where we don't have smart meters, and definitely in those cases having other IoT platforms will be can be much more cost effective. Definitely, I would agree with that.
Good. Another question for me: is there a big difference between winter and summer on the decisions made?
We could not really test during the summer period. Our testing mainly happened in the winter. It's not that we wanted to do it like that. Our original plan was to do it in the summer, but then due to delays and some other things, some personal things change, and we had to do it in the winter in 2022. In summer, I think the optimal times might change because of the solar generation profile. You may have a different demand profile during winter and summer because how the solar generation is taking place in different seasons. There is definitely an impact of seasonality, but yeah, and it would be nice if we could conduct this this implementation over the summer as well.
Yeah, I would imagine the results might be the same, but the timing will be dramatically different, I think. I notice with my system, it's very different in summer than now in winter.
Yeah, yeah.
How about including EVs? Can you put that into the system too?
Yep. we did not have, as you can imagine, we did not have enough participants who has electric vehicles, but that's another thing we are planning to consider in our next step of the project. That if the user has an electric vehicle, we can consider that, consider the demand of the electric vehicle without considering the vehicle to grid operation, but because that's a different story. But we can consider the demand of the electric vehicles and like when this is being charged and then how it is going to change our demand profile. Because if some user is trying to charge this electric vehicle during daytime or maybe during nighttime, then how it affects the optimal solution. There is definitely value in looking into these alternatives.
And can you extend it so that the EV could actually be providing power? Could that come into your calculations? So the EV supplies power to the house?
Yeah, I think currently we don't have the vehicle to grid kind of scenarios, and I'm not sure if you're if we should connect the electric vehicle battery to charge our other to provide power to our other appliances, if that is a good idea or not. So I think at this stage I would only consider it as a load. But over the time, when we have more matured solutions with vehicle to grid operation, V2G operation, then obviously we can consider it as a source rather than a load, just a load.
Yeah. Another question is, have you considered testing the use of the smart plug and notification technology against concurrent controls versus the historical data, which seems to be the control for this project?
We did not have any demand forecast integrated at this stage, but we do have demand forecasting algorithms which we are able to integrate, and perhaps in a future iteration we will be able to use the demand forecast rather than the historical data based on that. But it's not just the historical data. We are also considering the weather forecasts, and based on that we are choosing like what time will be the best for users to operate. And then for our evaluation mechanism, we are trying to compare before and after like 2021 and 2022's consumption to get an idea like whether things have changed because of our technology.
Yep. Good. Has anybody else got any more questions? That includes Chris and Howard too. Seems to me there's lots and lots of opportunities here, and we need to do this quickly. So I think that's the challenge for you, really. Challenge for us to try and support you to do it. The potential benefits, I think, are huge, but it's how do we get it off the ground as quickly as we can?
Yes. Yes.
Actually, I was wondering whether any electricity companies are interested in your work.
The network operators may not be that interested because their main focus is not the end users. They're more interested in maintaining their assets and so on. But the smart metering companies, they have an interest because this application can readily integrate with the smart meters, so they definitely have some interest in this project.
Maybe AEMO or other controlling bodies could be interested, particularly in moving load around.
Yeah. The thing is that when it comes to residential energy consumption, because the scale is less, many times people see that people don't see the value in it. But actually, if you think about, you have this many number of users in a certain suburb, in a certain city, then that savings will definitely be very useful. So I guess the mindset also has a role to play here, how they're looking into this problem.
Yep. Right, well, thank you for that, all the questions. Before I actually thank you, just a bit of other business items. This is our first one from Renew Melbourne, first webinar for quite a while. So we're quite keen to continue with them. So if people think it's a good idea and would like to help, we're very keen to have your input, either for ideas on what to talk about or doing a specific task on an evening or ongoing. Let Chris know if you're interested in helping. Renew wants to remind us that they have a tax-deductible end-of-year donations program. So if you would like to help Renew out, we'd certainly like that. We're planning our next meeting in August, which we're hoping will be a combined RMIT in-person event and also webinar. We're just going through all the challenges with the uni on that at the moment, but we'll keep you informed about that. And shortly we'll put up a poll for what you thought about tonight and ideas and such like. So that will be good. Well, thank you, Shama. It's a great analysis. I think there's great opportunities there. We can get it moving, as I say, quicker and more extensively.
Thanks for giving me the opportunity to talk about this. It was a pleasure.
Right, no, it was great. I always feel a bit sad on these Zoom meetings that you can't see all the people and hear them all clapping and such like. So thank you from me and thank you from all of us here. It's been a great night.
Thanks.
Thanking you. And to everybody else, there'll be a poll coming up shortly.